So in case of superconductors, there's a flow of electric current without dissipation. This is a very unique feature. So we can observe drop of resistance by 6 orders of magnitude, and also we can analogical effect in superfluid is flow of liquid without dissipation, without viscosity, and basically we have replacement of Ohm law with London equations. So basically London equations is about flow of electric charge is proportional to vector potential presence. So it's very much like in Schrödinger equation. And then there is occurrence of heat lambda transition both in superfluids and in superconductors. So when you measure heat capacity, there is characteristic increase and drop at the transition from macroscopic quantum effect to normal state. And yeah, so in case of superconductors, we have occurrence of isotope effect. We have various topological defects in superconducting order parameter, and they can be used or utilized for the purpose of information processing. So, for example, rapid single quantum flux electronics is using vortices as presence of vortex in superconductor as logical state 1, and its lag as logical state 0. So rapid single quantum flux electronics managed to construct the logical circuits that are very energy efficient. All right. What is more? So we have. All right. So we need to briefly overlook those features by detail. So there's short kind of motivation, which is actually a very big motivation. The universe in helium droplet is a very advanced book. It is probably one of the most advanced book I have ever met. So it's basically interlinks condensed matter physics, elementary particle physics, and cosmology. So it's not that easy, understandable book and papers. So perhaps you should review various types of papers on your own that also talks on this topic in more kind of user-friendly way. All right, so there are promises of so what's behind helium-3. So you see here this various types of physical phenomena. So you can study like quantum phase transitions. You can have transition from classical to quantum hydrodynamics. You can have a model of ITC superconductors. You can have implementation of black holes in condensed matter systems. Yeah, and neutron stars and so on. So there is bunch of phenomena that can be described, but we need to first start from the domain of facts. All right, so let me move on. Right, so that's very simple experimental justification of superconductivity. So essentially the occurrence of drop of resistance, which shows that some kind of order is induced. So it can be like order that can be, in Drude model, you can say that if relaxation times goes to infinity, then you can reproduce the features of superconductor. But of course, the fact is that there is like in superconductor, there is a liquid of superfluid electrons, you can say, that are they are kind of connected by one macroscopic wave function, like Cooper pairs. And there's another fluid. There's a fluid of normal electrons that are normal unpaired electrons that are not quasi-bosons, but they're just fermions. And so the same features might occur in case of superfluids. So basically, we have helium-3. In helium-3 is atom that is kind of quasi-fermion. So basically, the fermions can pair, and two fermions, when they pair, they become a quasi-boson. In case of superfluids, the situation is a bit better than in case of superconductors, because like helium-3 atom is neutral from electrical point of view. So essentially, because of that, you can say that these atoms undergo this so-called Bose-Einstein condensation in a more real way than in case of electrons. I need to basically we deal with this with these superconductors and superfluids. So essentially, there is the occurrence of this macroscopic quantum order parameter, and the key difference is that electrons in form of Cooper pairs, they become a quasi-boson. So this quasi-boson has a charge, so it can never fully go to Bose-Einstein condensate. And again, in superfluids, this achievement of this Bose-Einstein condensation is also not fully possible, because simply two atoms, they have distinct nucleus that is also charged. So simply it means that they can overlap only to a certain degree. So there is a much different energy scale of occurrence of this phenomena. So basically in case of superfluids, we need like 6 millikelvin or 3 millikelvin to the critical temperature to be achieved. And so superfluid, there's transition from normal state to superfluid state. So there is a pairing of helium-3 atoms at so two helium-3 atoms becomes a kind of boson, like at such temperatures. In case of superconductors, this transition occurs like in kind of classical superconductors on the level of kelvins. So there are like 3 orders of magnitude of difference in binding energy. So in case of superfluid helium, there is hyperfine interaction that is also important. And in case of superconductors, there is interaction between electrons and phonons. That is very much important mechanism behind the pairing of electrons. Okay, so let me move on. So so there are another features of another common features for both superfluids and superconductors. So you can create a Josephson junction in both types of systems. So for example, you have this the macroscopic wave function has a single value.
So after rotation around the loop, the wave function phase must be changed by multiplicity of 2 pi n. And in such case, you obtain the condition for quantization of vector potential, and from that condition, you obtain condition for quantization of magnetic flux. So you have presence of fluxons in the interior of a superconducting squid. However, in case of superfluid system, you don't have a magnetic flux, but you have a rotating container, and so essentially you get quantization of angular momentum, and so you can construct two superfluid Josephson junctions, and having those two superfluid Josephson junctions, you get integer values of angular momentum. And this is a very interesting system that can be used in space applications. So imagine you have a satellite, and in your satellite you install such superfluid squid. The satellite collides with some particle, small tiny particle, and this small tiny particle will change satellite momenta, and by very small value. And this change of momenta can be picked up by your superfluid squid. So that's a very nice area of application, and there is also nice area of analogies between two types of systems. Okay, so basically in superconductors, you have formation of vortices. So vortices are defects in superconducting order parameter, and those defects has a feature like almost like creation of particles. So so you can imagine that you have superconductor as the ground state as a kind of type of vacuum. So in ideal kind of ground state, you have no presence of normal electrons. You have all electrons are in kind of in Cooper pairs. Those from Fermi level that are in Cooper pairs involved in creation of Cooper pairs, so they are paired, and there is no magnetic field. So there is like vacuum, and suddenly you bring external magnetic field that is going to punch a superconductor in some small areas where superconductivity order parameter is smaller. So what happens is that simply there is presence of non-dissipative superconducting current around the vortex core. Vortex is the name of this topological defect, and basically these vortices, if they are far distance, they have a feature like particle. So two vortices with the same helicity, same direction of magnetic fields, they repel each other. And if they can, if they have a helicity that is opposite, so there's like closed loop of magnetic field. This closed loop of magnetic field will tend to, they will try to attract to such particles, and basically they will annihilate. So you have analogies of creation of particles and antiparticles in your system, and yeah, that's quite a nice feature. So the existence of this particle is kind of guaranteed by topological protection. So you have quantization of magnetic flux in each of these particles, and this simply you can have a multiple number of fluxons in one place, and at the core of this particle you have you have a order parameter of superconductivity that goes to 0. So this is so essentially I'm describing the existence of Abrikosov vortices. So this is basically the structure of the simplest approach. So you have superconducting order parameter that is C square, that is basically density of Cooper pairs. And if there is superconductor of second type, there is a possibility that magnetic field will punch superconductor in kind of local way, in point-like way. And in such case, there is profile of magnetic field of such shape. So magnetic field is killing the presence of Cooper pairs because simply it forces electrons in Cooper pair to rotate in the same direction. So basically it destroys the S superconducting order parameter. It can induce a little bit of triplet phase, but I'm not going to discuss on that. So essentially you have a situation where you can have multiple number of vortices, integer multiple number of vertices in one place. And then you have a quasi-classical levels inside the core of vortex core. All right, so let me move on. So basically, yeah, so there is very specific physics of excitations in superfluids and in superconductors. So for example, there is critical velocity of movement of superfluid. That's like velocity of light. This kind of analogical that no excitations in superfluid systems can move quicker. At the same time, there is maximum value of vector potential presence in superconductor. If you exceed this value, you are basically destroying this superconductor state. All right. So what are the nice other features that can be observed in both types of systems? So basically there is a tunneling effect between left and right superconductor. So there is you place left superconductor, insulator, and right superconductor. And so Cooper pairs can tunnel. And this is essence of Josephson effect. If you do similar types of, if you have a Bose-Einstein condensate, you can cut the kind of condensate into two parts, and there is a barrier via which tunneling also can take place. So you can have Josephson junctions in Bose-Einstein condensates and Josephson junctions in superfluids. So basically, you need to have a macroscopic quantum effect, and you need to be able to distinguish two subsystems, quantum subsystems that interact in a weak way. So that's basically a Josephson effect description in such type of systems. Very nice feature of this superfluids is that if you have a container with a superfluid, it can happen that your superfluid will crawl on the walls. So basically, you can have initially two different levels. So somehow this liquid will see this potential difference. So that's a kind of after a long time the system will equalize two levels of liquid. So this is so this flow in such type of system can happen without any dissipation. So this is this feature of superfluid flow that can actually look for the shortest path. That's a kind of quite unique feature. So this effect has no strict analogy in classical physics. I would say that only in classical physics, if you have a water with two levels difference, and only by creation of, if you create the water goes from liquids to gas form, then it liquidates, and after a long time, a similar effect can be achieved, but this is completely different time scale. So in a sense, the wave function somehow sees the whole system in a kind of holistic way. In a sense, wave function can feel this potential difference. So that's a kind of new feature added that is not necessarily present in classical physics. All right. So basically, the family of models, mathematical models behind description of superconductors and superfluids are very rich. So first level of understanding is always two-fluid model, coexistence of two phases, normal and superconductor, or coexistence of two types of superfluid in one volume. Superfluid so superfluid plus normal fluid. So coexistence of two types of fluids. This is not exactly fully theoretically correct, but it's first level of approximation, and somehow this picture works very well. Anybody that know how good is RCSJ model, resistor capacitor shunted Josephson junction model, is two-fluid model, but still it can parameterize your data, observational data, very well. So this phenomenology is very, very important in later insights to the systems under consideration. Obviously, next level is Ginzburg-Landau equations. So this theory of macroscopic wave function and microscopic order parameter. So you can have a density of Cooper pairs or density of superfluid, and this is, and here we are dealing with two nonlinear Schrödinger equations. So essentially, there is nonlinear term added to both equations, and the prominent feature is that there is different, I would say, geometry scale of this equation. So basically, when we talk about superconductors, we are talking about the kind of quantum correlations on the length of superconducting coherence length or longer, but that is around 3000 angstroms, so that's like 300 nanometers. And usually wave functions describing electrons, usually they are limited to very few nanometers. So that's a different time scale. There's another feature that that superconductors and superfluids ground state can somehow can protect itself from external excitations in the way that it tries to defend its ground state. So the such conglomerate of atoms is a little bit robust against changing of phase. So this also motivated many people why they supposed to implement qubits in superconductors and in superfluids, let's say, and not in other systems. Indeed, in case of superconductors, we have a situation of very low noise. It is like 3 orders of magnitude lower than in case of semiconductors. So that's very good argument for usage of Josephson junction and low temperature superconductors in quantum information processing. So higher levels of description are kind of more challenging, and I mean, you can you have to use it Eilenberger propagator or Gorkov propagator, and yeah, that's highly I would say connected with propagators theory. So you need to go to Kopnin books on non-equilibrium superconductivity or Petr-Valecka book as kind of introduction. And of course, most kind of abstract or general concept is the use of Kaldich propagator that has to do with imaginary time and with complex value time evolution. Maybe I will have a chance to talk about this during one of our seminars. And of course, this picture can be translated into path integral approach that can be a kind of equivalent in BCS theory, but actually it can have if you deal with the Kaddish contour, you can take into account dissipation processes that takes place. So there is essential enrichment of your mathematical structure that is able to describe your processes in more detailed way. All right, so let me move on. So basically we have a Ginzburg-Landau theory of superconductivity. It's very genius. This shows you the power of phenomenology over mathematization of duality, I would say, at some point. So essentially we have the assumption that there is a free energy functional F, and that is scaled by basically by density of Cooper pair. That is like C square, C modulus square is nothing else as density of Cooper pairs, and by square of this density, and there is some gradient of this density, right? And the thing is that alpha has negative value and beta has positive value, and they are both temperature dependent. And there's also this gradient term that you can imagine that this gamma is bit kind of scaled by 1/2 Cooper pair mass, more or less. So it's not surprising to construct such methodology of free energy, and simply yes, that's more fully expresses in that way. So there's also presence of vector potential and presence of magnetic field, and now you need to compute two functional derivatives of functional with respect to superconducting order parameter. So you obtain Ginzburg-Landau equation, nonlinear Schrödinger equation, or you can obtain this free energy functional derivative with respect to vector potential, and then you obtain the equations for kind of electric current, you can say. So that's this type of equation, right? So it's very essential that this theory has very simple methodology, and later it was like fundamentally from BCS theory it was described deeper. There was like Gorkov approach that Gorkov has derived Ginzburg-Landau theory from BCS theory. You can see this derivation like in Petr Valecka book. I would say that this derivation is it was done 20 years after Landau. So he was a candidate for a Nobel Prize, but he didn't get it finally. Anyway, all right. So let me move on. So the same type of thinking is also involved in a case when you deal with superfluids. There are various, obviously proposing free energy functional in such way is somehow mathematically justifiable in the way that is like Taylor expansion in terms of density of Cooper pairs, right? But of course, there is a hidden assumption here that you are close to critical temperature, so your superconducting or superfluid order parameter is not too high. So that's a hidden assumption. So you can forget about higher terms. All right, and then obviously, as I mentioned, you compute free energy functional with respect to wave function, derivative of free energy function with respect to wave function, and you obtained Ginzburg-Landau equation of superconductivity. Yeah, so alpha here is negative and beta positive. So such function will be minimized by non-zero superconducting order parameter. That's a phenomenology. This is this hot potential that you will see later. All right. So you here you have this picture. So you have free energy functional versus superconducting order parameter, and you see that indeed for non-zero superconducting order parameter, there are minima in this energy, free energy function, free energy, Helmholtz energy. Yes, indeed, close to critical temperature, your alpha can be scaled by T minus Tc over B. So this is value of superconducting order parameter in case of uniform superconductor with no occurrence of magnetic field. All right, so let me move on. So, and now this tricky part, so maybe I will go back. So it happens that having this Ginzburg-Landau equation, you can discover one of the solutions. That's this solutions for vortices. This was done by Abrikosov. So basically we have such solution, especially for a single vortex. You can do it by yourself as kind of exercise. Use kind of cylindrical coordinate system and try to solve it. So there is circulating current around vortex. Much more complicated case is so in real samples. In real samples, what happens is that you might have your superconductor can be punched via magnetic field, and this magnetic field will tend to go to such areas that has the smallest value of superconducting order parameter. So essentially, it can go by point like defects, dislocations in crystal lattice, magnetic impurities or non-magnetic impurities, and so on and so on. So basically, you have three stages of phase diagram of superconductor if you place this in external magnetic field. So first phase is so-called Meissner phase. You place a ball in very weak magnetic field, like in solenoid, let's say. So first response will be only screening currents. So there will be screening currents that will try to compensate the magnetic field that was imposed on superconductor from outside. So essentially, in such a way that there's almost zero magnetic field inside in the interior of superconductor. So this current densities are quite high, close to boundary between superconductor and vacuum, let's say, or non-superconductor. And this mechanism of Meissner shielding, let's say, works very well until certain strength of magnetic field and obviously for certain temperatures. If you exceed the value of magnetic field that you impose on superconductor, it might happen that your superconducting object will be punctuated in few places, and simply when it is punctuated in few places, there will be occurrence of vortices. So you will have two types of currents. So you will have a screening, like Meissner screening, plus you will have so you will have this Meissner screening, and let's say Meissner screening that is with red arrows, and you will have this another currents that will support the presence of vortices inside, right? Okay, so that's how it is. Yeah, so, and after, if you go further with magnetic field, obviously if it exceeds so-called critical value of magnetic field, or if you start to rotate superfluid with certain velocity above critical velocity, the system will suddenly go from kind of macroscopic quantum effect state to normal state, where there is no presence of this order parameter that is due to macroscopic quantum effect. And then when you observe various phenomena, these vortices can bend. When you send the electric currents, you can misshape them, you can entangle them. So a very good picture is this picture. So basically, if you have low concentration of vortices, like not so high, not so much magnetic field, when they're quite far away, they have features of particles. So they repel. So they can repel if you send the external electric current. You have a sample. There will be Lorentz force acting on these vortices, simply because each vortex is supported by a super current flowing around its core, and this current, when it's subjected to external magnetic field, there will be Lorentz force acting on it, right? So you can figure out that this Lorentz force is of such shape, and so it's perpendicular to both to current flow and magnetic field. So there is inevitable Lorentz force. There is so-called hydrodynamic. There's analogy with flow of ball in a liquid. So this vortex core is like a normal core, like a ball, that object with the normal phase surrounded by superfluid phase. And when this normal phase flows, so there are unpaired electrons in the core of vortex, and this vortices, this electrons feel electrical resistance. So there's some certain level of dissipation. So flow of vortex actually can be spotted by this current voltage characteristics very well, and there's some level of dissipation, which is already tricky in quantum mechanical description. All right, so there's also some kind of analogy with hydrodynamics. If you have a ball moving in a liquid, there is some kind of there is so-called Magnus force. So there is a force that tries to prevent you from a flow, from a movement. So it's like so this normal, the core of vortex that is moving is pushing around a sea of Cooper pairs. So there's certain kind of counter reaction of environment. So there's also Magnus force that is usually proportional to vortex speed. So it's like a kind of friction force. So all in all, and there's vortex over vortex force. So, and there's also, a very nice scenario is that around each vortex there's the flow of superfluid current, but also there's flow of superfluid current at the interior. So vortex cannot so easily move interior of superconductor. So there will be some another force that will try to prevent vortex escape of superconductor. Yeah, that's so you need to take account, and then in such a way you can in a sense, just using this Ginzburg-Landau equation, you can try to propose such types of forces acting on a vortex, and it becomes a kind of particle-like object. So there's also some kind of thermal force, like a kind of random force acting due to some random processes in superconductor taking place. So all in all, you can construct such particles, but these particles can have very peculiar properties. here is a very nice example of two vortices that are all kind of entangled. So there's one flux of magnetic field that is closed, and there's another closed loop. Around each loop, there is a circulation of superconducting current. So you can have various types of configurations of magnetic field. There is very extensive book or paper review by Blatter on vortex physics in high temperature superconductors. It's almost like 300 pages in length. Review of modern physics. You can spot this review by yourself. Yeah, there's a lot of issues involved with that. So, for example, if you have Josephson junction, there is possibility of tunneling of vortex. So, in the real way, it has a kind of features of particle-like. So, this is example of particle created from a vacuum that is ground state of superconductor, right? Okay, let's move on. There are certain analogies between, friction in classical systems, vortices in superconductor, and charge density waves. Charge density waves are just fluctuations of charge density in superconductors. I will not describe them in detail. There's a work of Professor Maeda, and this work describes physical regulators 2000. There's a physical regulators paper, and basically what are the analogies? So in case of mechanical, if you have a mechanical object and friction on the mechanical object is placed. So when there is mechanical object placed on the surface, there is some friction, and there might be some driving force if you want to maintain this object's speed. So you have analogies of driving force like mechanical force, and there is counterpart is Lorentz force in case of vortices in superconductors. Then you have critical parameter for static friction, maximum static friction, and here you have critical current density. And there is viscosity, like hydrodynamic resistance, and dissipative flux flow. So, and many other terms, many other features like the case of thermal fluctuations are important in superconductors, but not so important in mechanical object movements. Anyway, so that's a very tricky way that in a quantum system we can introduce, by studying dynamics of vortices, we actually study the dissipation in quantum systems, and this is a very tricky thing. So that's not that straightforward. Okay, let me move on. Okay, now let us move to more concrete example of vortices in superfluid. So we have this cylinder. Let's say we have a metallic cylinder, and this cylinder is in the cylinder we place the superfluid helium, and what happens is that we start to rotate this superfluid helium, and actually so the speed of rotation is, so the system is somehow equivalent to the system of superconductor placed in magnetic field. So your rotation speed is like vector potential, more or less. And then there's a formation of vortices in superfluid helium. So obviously, we will have such situation as here. There is a superfluid vortices. So angular momentum is quantized, and you can have formation of three, for example, superfluid vortices, 4, 5, and so on. And also, you will have such such effect that these vortices will also repel each other, right? And yeah, so this is how this is experimentally done, and then it's somehow, I would say, almost like halfly accessible by naked eye, that these vortices, so the superfluid, so it's like, this is like very good picture of how quantum wave function is kind of formed. So if you rotate this the cylinder with superfluid, what you have a velocity versus radius, and indeed you can see such dependence, and this is so zero angular momentum is inside, and this is first kind of first level of angular momentum to two, and so on. So this is due to multiplicity of Planck constant, right? So this is this postulate from Bohr model of atom that angular momentum is multiplicity of Planck constant, and this is here visible on macroscopic scale. Obviously, you can change, you can force this dynamics of rotation. You can make this rotation to be time dependent, and doing so, we have the situation where you can create very complicated dynamical state of a system, and then you can create entangled vortices, and that's how it is. All right, I move to more concrete examples later. Okay, this is two-fluid model. So this is the way how to make a marriage of superfluid liquid of electrons and normal liquid of electrons. So the superfluid is by this term of current, and the others are normal. It's concept of washboard potential that I already discussed before. You can obtain Gross-Pitaevskii equation by assuming that atoms that you have atoms with point-like interaction, and there's some effective potential, external effective potential that is kind of keeping the condensate in certain region of space. So point-like interaction is by this Dirac delta function, and basically it leads you to such Gross-Pitaevskii equation, and such equation for electric current. So not electric current, the flow of mass. Since you have no electric charges in a superfluid, you have mass currents, not electric current. You have electric current in superconductor. Okay, and there is a chemical potential. So you have nonlinear term in Gross-Pitaevskii equation that only comes from atom-atom interactions. So obviously you can, choosing different types of condensates, you can tune it, right? You can follow more in more detailed way its derivation in Fetter-Walecka book on many particle physics. I think it's pretty well done. Obviously, there are many other books as well. All right, so the existence of this, I would say, the existence of superconducting order parameter was obtained in a very phenomenological way, and we can go into more microscopic picture. And this microscopic picture first it has emerged for the case of superconductors. In 50s, there was created a theory, Barden-Cooper-Schreifer theory. So Cooper has created the concept of Cooper pair that since we have a very high density of magnetic field, it can be only judged from the point of view of kind of Bose-Einstein condensate, right? So, so he suspected that there is a kind of condensate in superconductors, and this condensate can only be created if we move from fermion statistics to boson statistics. So the only natural way of doing so was finding the way that spins can Cooper pairs or objects that are kind of made of multiple Cooper pairs at the same time that were proposed. However, full description with use of Cooper pairs was sufficient. So it turns out that two electrons can have integer angular momentum, and there could be projections of, and then there's so-called S wave and D wave, singlet superconductivity. So total spin of Cooper pair is 0, or total spin of Cooper pair is 1. There's a triplet phase. And then two electrons obey a kind of Bose-Einstein statistics, but obviously you have to take into account the fact that electrons are still charged. So this Bose-Einstein condensate goes only to a certain level and then it stops. Anyway, you obtain such equations of motion as given here. This is original Hamiltonian. And then basically, there is a mean field description of BCS theory. This mean field description allows you to write in such a way that there is two creator and two fermionic creator and two fermionic annihilator operator can be effectively described by two creator and two annihilator fermionic operators multiplied by some effective complex value field. This is essentially this level of description. Yeah, that seems to me that there is a necessary. Yeah, so we have such situation as here. So there's two creators and two annihilators. Yeah, so the problem is reduced from 4 operators, fermionic operators, to 2 fermionic operators. So effectively, your Hamiltonian becomes like mean field Hamiltonian. And this mean field is density of Cooper pairs, basically. So what you have here is kinetic term. And there is superconducting order parameter complex value field. This derivation is quite well done in Joseph-Spalek book. No, obviously in many other books like Petr-Valetzka. So effectively, you have superconducting order parameter that is a mean value of 2 annihilator operators. So originally you have such potential in second quantization, and this is reduced to a such form. So having equations of that form, mean field Hamiltonian, what happens is that you can actually go into next level. So okay, yeah, to rewrite this annihilation or creation operator by two Boglie-Bonn operators, gamma I and gamma I daga, and effectively, when you construct a Hamiltonian, you get very analogical situation with harmonic oscillator, and this leads you. So this leads you directly to Bogoliov-Dijon equations. In Bogoliubov-Dijon equations, you have Hamiltonian of free particle acting on an electron wave function. There's superconducting order parameter acting on whole wave function times. So this is a set of two coupled equations of such form. So you can write them in such a way that there is a superconducting order parameter on its antidiagonal, and there H0 is Hamiltonian of free particle for electron and hole. So this equation has a lot of analogies with Dirac equation. Actually, it has very much a bit similar structure, but so electron and hole, they play a role of particle and antiparticle. All right, so let me move on. So basically, so this concept of Bogoliubov-Dijon equations is very powerful. In particular, it can also describe you the topological states of superconductor. So if hole and electron are exchanging their roles, or they are the same, let's say, then you have possibility of existence of Majorana solutions. Also, there is the whole physics is invariant under global phase transformation when you add a phase both to electron and to a hole. Yeah, there's also, I will now go to the description of this energy spectra. So before that, we deal with such equations. So we have two coupled equations. So hole and electron are coupled by means of superconducting order parameter, and that's there are the constraints written in such a way. So there are two coupled equations, and there is self-consistency relation. And if we refer to the picture of you can say that we have a vacuum, and on this vacuum there is action of, and so your real quantum state is made of the wave function of electron and hole. All right, and now I move to these analogies of let's say between the relativistic physics and physics of macroscopic quantum effects in superfluids and in superconductors. So we need to find the excitations in the Dirac equation. So there is superconducting order gap delta square, and so this plays role of mass in special relativity by Einstein, right? And then there is this kinetic term. In case of superfluid, it's in such a form, and there is p square here, right? So basically, this presence of, so this gap is like a mass of particle. the situation becomes much more complicated when we deal with two types of phases occurring in helium-3. So actually what we have is helium-3b that has isotropic order parameter. The order parameter that has a kind of rotation symmetry, right? So it doesn't depend on direction in which we go. It's in helium-3b. And in helium-3a, we have order parameter that is isotropic. So there are some nodes at which the order parameter is kept 0. If we apply a kind of Bobov-Digen's equations for the system, we get much different excitation spectrum. So in a sense, in this isotropic helium-3b, we got excitations that are a bit similar to the structure of excitations you obtain from Dirac equation, and thus we can talk about Dirac vacuum. And in case of helium-3a, the energy, so there's a linear dispersion relation, so there is E is C times P. So essentially this is like a photonic mode. So you get a different types of vacuum. And then this is quite interesting to know that there is this coexistence of those two phases in one container. It's absolutely possible from experimental point of view, and I would try to picturize this situation in more detailed way, having some references to some experiments. So basically, in helium-3, the excitation spectrum is much more richer than in the case of superconductor, simply because there is no crystal lattice in superfluid systems, and this brings enormous complications. This brings richness of various types of phases that are occurring. And yes, so you see this, and energy spectra of this Bogoliubov fermion is given us by a second equation. So the dispersion curve is much more richer in case of superfluid systems. So we have the Fermi quasi-particles and protons. So that's the various contributions of various physical effects are described on the given picture in more detailed way. All right. Let me move on. So basically, in discovery of high temperature superconductors by Bednosh and Miller was very nice example of superconductors with isotropic superconducting order parameter. It has the situation is quite analogical to the case of two types of phases in helium-3. So D-wave superconductors have so-called D-wave. So like Most traditional superconductors has isotropic superconducting order parameter S. So it's only described by complex value field. And in case of D-wave superconductors, we have two complex value fields. And there are some nodes, some directions in space, as given here, where superconductivity order parameter goes to 0. And we can construct or propose Volovik-like equation for such type of system, and that can be expressed by Pauli matrices in a such way as given here. You see that there is very kind of abnormal dispersion relation present here. All right, so you can have a richness of this energy spectra in various types of superconductors, and you can draw some analogies between superconductors and superfluid systems. Yeah, so basically, maybe I should stop right now and take some questions from you, and I can suggest that continuation of this seminar like next week, right? So please let me know on your type of questions. All right, so hello? Yeah. All right, so if there is no questions, I suggest that we can continue next week. So have a nice weekend and see you next week on second part of this talk. So I believe that's quite lengthy content, and then it requires a lot of attention from all sides. All right, thank you for your presence.
Thanks.